Hello everyone, welcome to the next session of Strength of Materials. In this session, I am going to discuss about some more numericals on bars with varying cross section or bars which are subjected to loading at the junction. In figure below is shown a steel bar of cross sectional area 250 mm square held firmly by the end supports and loaded by an axial force of 25 kN. Here you can observe L-N-M is the bar. At the junction N there is a loading of 25 kN. The area is given to me as 250 mm square. At L and M are two fixed ends. If I remove the fixed, there will be two reactions which is shown as RL and RM. The direction has been given to me. I have to determine the reaction at L and M, which means I have to find RL and RM. And the second thing that I need to find is extension of the left portion, which means I have to find extension of LN portion. So this is the first thing and this is the second thing which I need to find. The first thing that I need to observe is RL and RM is unknown. So I will use the equation summation of force along x-axis is equal to 0. Any force moving towards right is going to be positive according to my sign convention. I can observe RL goes towards the left, so minus RL. 25 goes towards the right, so plus, and RM goes towards the left, so minus RM is equal to 0. I can also say RL plus RM is equal to 25. This is equation number 1 which I obtain. Now when I look at Ln and Mn, these two sections, I will observe that for Ln to the left I can observe an extension kind of effect, which means there is an elongation tensile effect. So obviously to the right also will be a tensile effect, which will be 25 minus Rm. I also have to take up Rm at this position and understand its effect. So I will only look at the left hand portion. So I can write down that there will be a extension because I can clearly see that there is a tensile effect over here. So extension in Ln will be delta L Ln is equal to PL by EA for Ln. If I substitute, the value of P is going to be RL, the length is 250 mm, the value of E is known to me 200 giganewton per meter square. I will leave E as of now, and the area is 250 I know. So if I want I can substitute or I can leave it as A. There is a reason why I am leaving like this. So I will just mark it as equation number 2. Now looking at NM portion, I observe that one end is showing me compressive type of effect, which means at this end also there will be a compressive effect. So let's write down the compression or the contraction of NM portion. I'll have contraction of NM is equal to delta L NM, which will be PL by EA for NM. The value of P will be RM. The length is 600 and the rest I leave it to EA and I mark it as equation number 3. I am writing as E and A because E is same for both the sections and area is also given 250 for both the sections. So I am leaving it as EA. As of now, next we will observe something. These two ends are fixed, which means whatever extension happens in Lm will be equal to the contraction in Nm because there is no sign of yielding of the supports and it is clearly written that these two are fixed ends. So I can assume that extension of Ln will be equal to contraction of Nm. So let's write down the equation. I have RL into 250 divided by EA is equal to Rm into 600 upon EA. You can observe E and A gets cancelled on both the sides. So I can write down RL is equal to 600 upon 250 Rm. So if you solve this, you will get RL is equal to 2.4 Rm. And when I substitute this equation 4 in equation 1, that is RL plus Rm is equal to 25, I'll get the value of RL as 17.647 kilonewton and I'll get Rm as 7.353 kilonewton. So these are the two answers that I get, and the last thing which I need to find is extension of left portion, which is extension of Ln. As you can see the formula over here, it is RL into 250 upon EA. RL is 17.647 into 10 raised to 3. The value of length is 250. E is given as 200 giganewton per meter square. When I convert into Newton per mm square, I'll get 2 into 10 raised to 5, and area is given as 250. When I solve this, I get the value of elongation as 0.0882 mm. So this is how I solve this numerical. Now let's take up another one. A straight uniform bar AD is clamped at both the ends. You can see both the ends are fixed over here and loaded as shown in the figure. At B and C there is a load of 5 and 10 kilonewton respectively. Initially the bar is stress free. Determine the stresses in all the three parts AB, BC and CD, which means three parts, if the cross sectional area of the bar is 1000 mm square. So the area is common, it is 1000 mm square, and I need to find stress in AB, stress in B to C and stress in C to D portion. Now for solving, the first thing which I need to do is I need to find out two reactions at these points A and D. I will assume the direction. I have no hard and fast rule for assuming these directions. I assume both go towards the left because B and C are shown towards the right. It is possible that RA is towards the left and RD is towards the right. It will be proved once I find the value of RA and RD. If I get positive values of RA, RD, my assumed direction is correct. If I get a negative value for either of the two, then I will say that my direction assumed is wrong and it will be the opposite direction. So let's solve and find out what is the exact direction. I do not know, I am just assuming. Now the first thing that I will do is summation of force along x-axis is equal to 0. Force is going towards right, I assume as positive. So RA is going towards the left, 5 is going towards the right, 10 going towards right and RD going towards left is equal to 0. I can write down RA plus RD is equal to 15. This is my equation number 1. Next, if I observe very carefully here, without even drawing the FBD, I can still solve this numerical because AB has one end as extension. Since there is extension in one side, obviously AB is subjected to tensile kind of effect. If I look at CD, D is subjected to compression according to me right now. So I will write down that the third portion is subjected to compressive effect. Now when I solve for B to C portion, it can be tensile or it could be compressive. I am assuming this as tensile. Okay, I'll draw the FBDs. This is A to B. One side is RA. On the other side, if I draw, it will obviously be tensile. I have 5 pulling the section plus 10 pulling the section and RD is compressing the section. So I get 15 minus RD to the right. When I talk about section C to D, To the left I have drawn RD as compressive. So obviously from this end also I am going to have a compressive effect. When I stand at the middle of CD and I look to the left, RA is positive, 5 will create a compressive effect and 10 will also create a compressive effect. So I will have RA minus 15. Now last comes B to C portion. If I look to the right, I will see 10 kilonewton pulling and RD is compressive type. When I look to the left, I will see RA is creating a tensile effect over here and 5 is creating a compressive effect. Now looking at these two numbers, I assume that it is of tensile type. If I get positive answers for RA and RD, then I would say that my assumption is correct. If not, I will say my assumptions are wrong. Now for the first one, let me say that the change in length is delta L1, for the middle one delta L2, and for the third one it is minus delta L3. It is negative because it is of compressive type. The first two are of tensile type, so they are positive. So let me write down the equation. Extension of AB will be delta L1 will be PL upon EA. So here the value of P will be, if you look here, it is only RA, the length is 600, the value of E is not known to me, so I'll leave it as E, and the value of area is given to me as 1000 mm square. Next is contraction of CD. This is delta L3 will be PL upon EA for the third bar. So let me write down the value of P first. It is RD. So I'll write down RD into the length is 400. Let me leave E as E and area is 1000. And the final one is extension of BC portion. This is delta L2 will be again PL upon EA for the second one. The value of P, if you look here, it is RA minus 5 or 10 minus RD. You can take either one of the two. So I am taking RA minus 5. The length is 500. Value of E is E and area is 1000. So this is how I have written for all three of them. Now let's look at the figure once again. If you observe, AB is under extension, BC is also under extension, CD is under compression. Can I say that the extension of these two will be equal to the compression of CD? In other way also, I can write down delta L will be delta L1 plus delta L2 minus delta L3, and this total change in length will be 0. So in that way also it can be written, or I can directly shift this over there, or I can write delta L1 plus delta L2 is equal to delta L3. So this is also another way of writing. So let's substitute the values and get the answer. Delta L1 is RA into 600 upon E into 1000 plus delta L2 RA minus 5 into 500 upon E into 1000 is equal to RD into 400 upon E into 1000. Now if you observe, E into 1000 is common here and here as well. So this term actually gets cancelled out. So what remains is 600 RA plus 500 RA minus 2500 is equal to 400 RD. So I get 1100 RA minus 400 RD is equal to 2500. So here I get equation number 2. So when I solve equation 1 and 2 simultaneously, I'll get the value of RA as 5.67 kilonewton and the value of RD is 9.33 kilonewton. So these are two answers that I get. Using this, I can calculate the stress in part AB, BC and CD. So if I have to calculate the stress in part AB, which is sigma AB, will be load in AB upon area. So load on AB portion, if you see the diagram, on AB portion the load is say RA. So the value of RA is 5.67 into 10 raised to 3 divided by 1000. So stress is 5.67 Newton per mm square. This is tensile. So this is sigma AB. Now next is stress in part B to C. Sigma BC is equal to load of BC portion upon area. Let's look at the figure. The load is either RA minus 5 or 10 minus RD. So let's take up RA minus 5. It will be very simple because it is 5.67 minus 5, which is 0.67 into 10 raised to 3 upon 1000. So I get the answer as 0.67 Newton per mm square. I had assumed this was tensile and I get a positive answer. So my assumption is correct. And the last thing is stress in part CD, which is sigma CD, will be load in the CD portion upon area. If you observe here, RD is the load. So the value of RD is 9.33 into 10 raised to 3 upon area is 1000. So I get the value as 9.33 Newton per mm square, but this is of compressive type. I am not using a negative sign. I will just mention that it is compressive, which will indicate that it is negative. Let's take up another problem. For the bar shown in the figure below, calculate the reaction produced by the lower support on the bar, which means I need to calculate R2. Take the value of E as 200 giganewton per meter square. So this will be 200 into 10 raised to 9 Newton upon 10 raised to 6 mm square. So this will be either 200 kilonewton per mm square. If required, I'll use this, or it is 2 into 10 raised to 5 Newton per mm square. For safer side, I'll write both of them because in these kind of problem, the reaction value will be in kilonewton. So you never know, if you are writing the equation and you want to use the value of E in kilonewton, then it is very easy to use, and in case I don't need it, it gets cancelled out because of any reason. So I will solve in both and I'll keep it ready. So it becomes faster when I solve the numerical when I am appearing for any examination. I need to find the value of R2. That's the only unknown. Okay, I also need to find the stresses in the bars, which means I need to calculate stress in LM and stress in MN. Now R1 is the reaction on L portion, and this reaction is something different than the reaction which we have seen priorly. That is, this value of reaction will come into picture only when this portion of N touches this end. So we are going to assume that this N touches this portion because of this load 55 Newton which is applied at this junction M. So because of this load, this gap is filled. This value of gap is also known to me. The value is 1.2 mm. Okay, now if you look at LM portion, you will observe that it is under tensile effect because one side is definitely showing tensile effect, and because of the load, obviously this gap of 1.2 meter is filled, and this bar will now show compressive effect because this side is clearly showing compression. So obviously this end also will have compression. So I can write down that R2 comes into picture if N touches the base, which is this end. Okay, so I assume that it is coming into picture. Now I will take summation of force in y direction is equal to 0. Here if you observe, the forces are along y axis. So I will assume upward direction is positive. So R1 positive minus 55 plus R2 is equal to 0. Therefore, I can write down R1 plus R2 is equal to 55. Let's mark this as equation number 1. Next, I'll write down the extension of LM portion and the contraction in MN portion. Will be delta L1, say, so it will be PL upon EA for the first one. The value of P, on one side I can see reaction R1, the length is 1.2 meter, which is 1200 mm, and I have the value of E as 2 into 10 raised to 5. Suppose if I am using Newton and mm. Now here the load is in kilonewton, so I will take it as 200. I hope you understand this because of this equation. When I have to use this equation, this value of 55 is in kilonewton. So by chance if I use E as 2 into 10 raised to 5, there will be a clash of units when I have to say use simultaneous equations or substitution method, which we generally use. So here I am taking E as kilonewton per mm square. So mm gets adjusted here and kilonewton will get adjusted with this R1 value. And the area is known to me as 110 mm square. So here I will write down 110. So this is for LM portion. Let's write down the contraction of MN, which will be delta L2. Again PL upon EA for the second one. Here I have reaction R2 into the length is 2400 divided by the value of E is 200 and the area is 220. Again I will write down delta L, total extension, is equal to delta L1 minus delta L2. This will be of compressive type, so it is negative, and this is of tensile type, so it is positive. Total extension is very important in this question. In the previous question it was 0, but here if you observe, there is some extension or there is some change which is taking place. So this gap, which is 1.2 meter given, is the data which I need to use for the total elongation of the bar. So here I write down 1.2 is equal to R1 into 1200 upon 200 into 110 minus R2 into 2400 upon 200 into 220. So here I will get 1.2. You can observe 200 is, sorry, this is 200. So 200 is common for both of them. So I'll write down 200 here, and 110 is also common for both. So here what remains is R1 into 1200 minus R2 into 2400. Now if 110 is taken out, so what remains in the denominator is 2. So this becomes R1 into 1200 minus 1200 R2, and here I have 1.2 into 200 into 110. So I have R1 minus R2 is equal to 1.2 into 200 into 110 upon 1200. So therefore R1 minus R2 is equal to 22. I mark this as equation 2. If I solve equation 1 and 2, I get the value of R1 as 38.5 kilonewton and R2 as 16.5 kilonewton. So these are the two values of R1 and R2 that I have obtained. Now once I have obtained R1 and R2, it is very simple to calculate the stresses in LM and MN portion. Stress in LM will be load upon area. The load is R1, area is A1. R1 value I have got as 38.5 into 10 raised to 3 and area is 110. So I get the answer as 350 Newton per mm square. And if I have to calculate the stress in MN portion, I will use R2 upon A2. R2 is 16.5 into 10 raised to 3 and area is 220. So I get the answer as 75 Newton per mm square. With these three numericals, I'll stop this session. I'll continue with two more numericals based on the same topic and different applications in the next session. I hope you have understood these numericals. If you have any doubt, write to me in the comment section. Don't forget to like, share and subscribe to my channel. Hit the bell icon for latest updates of my videos. I'll see you in the next session. Thank you.